In this lesson, we're going to be taking a look at a small but important part of the R language, namely how it deals with missing data. Now, in real-world data, missing values are unfortunately a fact of life. It is very rare to have a data set where everything is always measured. Usually, some things are impossible to measure or the measurements get lost. So for some reason, some of the data will be missing. And what we're going to be looking at is how we can deal with this. So R is actually a programming language that was developed by statisticians for statisticians, and this means that missing values are a built-in feature of the language, which incidentally makes it quite unique. Most programming languages do not have missing data as a built-in feature. Either one has to implement one's own version of them or do some other kind of workaround, which makes it a bit complicated. That is not the case in R. In R we have missing values built in right from the outset. Missing values are denoted by NA, spelled with capital N and capital A, and that stands for not available. And this is one of those reserved words or reserved symbols in R that you cannot use for any other purpose. So just remember that. When you see capital N, capital A, that just stands for missing data. What happens if we try to perform operations on missing values? Well, the point is that a missing value represents some sort of uncertainty. A missing value could have been all sorts of values, and this uncertainty is propagated through when we try to perform operations on missing values. So for example, 4 plus a missing value, 4 plus NA, is itself equal to NA. It will result in another NA, and the reason is logical. The NA in the expression 4 plus NA could stand for anything. It could be any number, so we don't really know what the result is, so we just say that it is also not available. The exact same thing is true for any functions that are built into R. So for example, as you can see, if we apply the square root function to an NA, then the result gets propagated, meaning the uncertainty gets propagated, and the result is itself an NA. Now, this is true even in cases that you might find tricky at first. If we type in NA is less than NA, then your initial thought might be that this is supposed to be false, because NA is clearly equal to itself, NA, so it cannot be less than itself. But here's the trick. The NA on the left side of the less than symbol and the NA on its right side are not necessarily the same thing. They simply represent missing data, and we do not know whether one is greater than the other, or maybe they're equal to one another. Therefore, when we do such a comparison, the result will still be NA. And maybe most surprisingly, but exactly for the same reason, NA equals NA also returns NA, and not true. It is not true that NA equals NA because the two NAs on the two sides of the equality symbol might not represent the same missing value. So this is very logical, but it is something that is quite important to keep in mind. To illustrate this idea, here is a small example. So let's look at this simple two-line program that we have on the screen. The first line of this program defines a variable called result, and it uses a function that we haven't talked about yet, but it is a very useful little function. It is called sample. What sample does is it gets an input which is a vector. In this case, you can see that it is a vector comprising of the NA, so missing value, not available data, and the number 0. So it's a two-element vector. The first element of the vector is NA, and the second element is 0. And then it has another argument called size, and that is the number of elements that we are going to be sampling from this vector. So all we're saying here really is that we have this two-element vector, either NA or 0, and we sample one of them randomly out of this. So it's not predictable which one will be drawn this before we run this program. So it could either be NA or it could be 0 with equal probability, 50-50 chance. So result is either NA or 0, and we don't really know what it is after running that line just yet. Then the second line of this program consists of an if-else, where we check whether the result is an NA, with is result equal to NA, and if it is, then we return the character string missing value, otherwise we return the character string 0, so basically representing what the result is. Unfortunately, for the reasons just discussed, this does not work. And the reason this does not work is because if result happens to be an NA, then the if-else is testing whether NA is equal to NA. And as we've just discussed, that itself does not result in true or false, but results in NA itself. So because it results in NA, the if-else function itself fails and just returns NA. It propagates the uncertainty. So this is not how we check whether some result is equal to NA. Instead, to do that, there is a convenient built-in function called is.na. And this is the function we have to use if we want to check whether some result is actually missing. You see on the slide the same program as above, rewritten. The only thing that's different is that in the second line, instead of result equals NA, we have is.na result. And this will now work. Is.na result returns true if result is NA and returns false otherwise. So in this particular case, we see that what we get in the text is missing value. That's the output as a character string, which must have meant that is.na result evaluated to true, because if you remember, the way the if-else function works is that if the predicate in the first argument turns out to be true, then it's the second argument that's returned. Otherwise, it's the third argument that's returned. So since it was the second argument missing value that was returned, that's why we know that is.na result must have evaluated to true. So result must have been sampled to be NA in this particular case. So the principle that R tries to follow is that no missing value should go undetected and untreated. So it tries to make it explicit that you need to treat values that are missing. This also means that if we use any of those summary functions that we learned about in the last lesson, namely those that take a vector as an input and then aggregate them into a number, if there is any missing values in those vectors, then the functions themselves will return missing values unless otherwise instructed. So here's a little example. We call a vector measurements, which represents measurements of something, doesn't matter what it is. It's simply a vector comprising of the numbers 36, 47, and then there's a missing value, then there's 25, then there's another missing value, then there's 12, and finally there is 40. And if we try to take the arithmetic mean of all of these values, then what we get back is an NA, a missing value. Why? Because if there's even just one NA, that is missing value, in the vector, then that will propagate the uncertainty and the lack of knowledge about that piece of datum throughout the computation, and therefore the best that the mean function can do is just to return that it does not really know what the result should be, that it is an NA. We can override this behavior. There is an argument to the mean function that reads na.rm, which is short for na remove. So remove all the NA values. And that argument by default is set to false. But in this case, if we explicitly add the argument na.rm equals true, and thus set this removal to true in the mean function, then what will happen is that all the entries of the vector that are equal to NA will be discarded. So in this particular case, in the measurements vector, those two entries, the third and the fifth entries that are NA, those are discarded, and we're only left with the 36, 47, 25, 12, and 40 as entries. And those are the 5 entries that the mean will be then taken over, and then we get the result 32. Important to note, all those other functions as well that we talked about last time, like variance, standard deviation, minimum, maximum, median, and so on and so forth, you can check the last lesson to look at those functions. All of those have an na.rm argument. So if we want to ignore the missing values, we can do that, but we have to be explicit about that. And this is a very important property of R. It requires us to be explicit if we actually want to ignore missing values. It does not allow us to ignore them silently. It will always propagate the uncertainty caused by missing values through the functions unless we explicitly tell it not to do so. Apart from missing values, there are some other weird results that one can get that are useful to know about. One thing is, what is, for example, the logarithm of 0? Well, you might remember from your mathematics studies that the logarithm of 0 is actually minus infinity. And that is in fact what the computer will return. If you type in log of 0, it will actually return minus inf with a capital I and lowercase n and f. That is short for infinity. So yes, when one does a computation that technically results in mathematical infinity, then the computer will return this result, which is not really a number, it just denotes the fact that the computation did not result in a proper finite value. Another thing that can happen is that we get a result that is denoted NaN with capital N's and a lowercase a, and that is short for not a number. So an NaN means not a number. When can this happen? Well, for example, you know that square roots and logarithms are only defined for positive numbers, at least if we want the results to be real. There is a way, by the way, to treat complex numbers in R. It's not even very difficult to do so, but I'm not going to go into that here, so don't worry about that. And if you have never heard of complex numbers, then you especially shouldn't worry about this. I'm just noting that it is in principle possible. Let's just now remain with good old real numbers. You might remember that the square root of a negative number doesn't exist, and the logarithm of a negative number also doesn't exist. So if you, for example, try to compute the logarithm of -1, you will get back the result not a number, which means that it's not a missing value. It's not that for some reason this value wasn't entered somewhere. It's just that the expression was evaluated and the expression did not evaluate to a proper real number. And that's when we get this result NaN. So for example, as you can see, if you type in log of -1, then you will get back NaN. NaN is not very different from Na. So it actually works very similarly in many ways. In fact, the na.rm argument of functions that have that argument works just as well with NaN as with Na. Here's a little example. If we have a vector x, which is just a simple vector with the numbers 1, 5, and then an NaN and 3, then if we try to compute the average of these numbers, then we get NaN again. The ignorance about that number, the absence of knowledge, gets propagated through. And we have to handle this explicitly, but we handle it explicitly in exactly the same way as we did it with Na, namely just add the na.rm equals true argument to the mean function. That will make it explicit that we want to ignore NaN values as well as Na values, and then we get the result that's 3 because it is the average of 1 and 5 and 3. The same is true for all the other functions as before. So the na.rm argument, which all these other functions like variance and standard deviation and minimum and maximum and median and etc. also have, will also remove the NaN values and not just the Na values. So that is all for this topic. Again, it's a small but important one because we do need to know how to deal with missing data, as missing data are a fact of life. Real data sets will always have them, and therefore we need to know what to do when we're confronted with them, how we can take them into account, and how we can ignore them if that is what we want to do. So thank you for your attention, and we will meet again next time.